Let me state divergence theorem, and then I will compare and contrast it to the Stokes theorem. What is the difference to begin with is that here we have a closed surface. Unlike in Stokes' theorem, where we had the boundary, our surface had a boundary, here there is some volume inside the surface. So think about an ellipsoid. So the surface is the shell around this volume. So E is volume, the 3D space inside it, and S is a closed surface which encapsulates it. It's 2D, it's just the shell. These are not too easy concepts, to be honest with you. If you dig deeper, you can run into questions. For example, maybe this surface has a twist in itself. It's kind of knotted. And you can think about a torus, for example. There is an empty void inside, although it also encapsulates some volume. Is it allowed or not? So, but these are, of course, questions that we don't concern too much in undergraduate calculus. So all we want to say is that the whole thing is simple. So the book says simple region, simple volume. What that simple means is quite involved, to be honest. So anyway, we have no twists and no crazy geometry going on. We have just a shell, and inside that there is a volume. Divergence theorem relates a 2D integral to a 3D integral. So you are given any vector field defined on a region which is larger than the whole volume, and so everywhere, including on the surface and a bit actually off the surface and in the interior, there is a vector field. No other assumptions on it other than just having enough derivatives. And my two integrals indicate that I'm doing a double integral. So I'm doing a double integral over the shell of this surface. So that's a two-dimensional integral, a surface integral in the sense of section 16.7 that we have talked about so much and is familiar to us from Stokes' theorem. Divergence theorem claims that this surface integral is equal to a triple integral in the inside. That means the volume that is inside this S of a derivative of f, and that in this case is divergence of f. This is a scalar function, so I don't need to dot with anything. It's just a real valued function, and I simply integrate it. So that's the message of divergence theorem. I must say here that provided S is oriented outward. Here also it's assumed that this surface is orientable, and that for the orientation we choose the one that is pointing off the volume. So if you are on the surface, the normal you will pick will be this one, not its minus. So at every point. So for surface integral, what we do is we dot product this f with the normals, remember, and integrate. Yeah, I mean, that's all about divergence theorem. Let me show you a second proof of a previous claim that I had made. I had claimed that on a closed surface, if you integrate a curl, then you get 0. Previously, when we proved it using Stokes theorem, we used this kind of ingenious trick that you cut out a small disk, and now it becomes a surface with a boundary being the boundary of this disk. And then we wrote the Stokes theorem, which says the integral away from this disk equals integral on the boundary of the disk, so on the tiny circle of FDR. And we then took a limit by taking a smaller and smaller radii, and because this goes to 0 and the other side goes to this quantity, it must be 0. But that was a tricky argument. Let's see how divergence theorem helps prove this claim. So by divergence theorem, this integral of any vector field, in particular curl ds, is equal to integral within the region of divergence of that vector. So this will be divergence of the curl of f vector. And it is very well known that if you take curl and then divergence, then you always end up with 0. So this is integrating in the interior the scalar function 0, and that is 0. So that's the second proof that I had previously promised of this fact. Here that doesn't happen because f is not necessarily in the shape curl of f. So if f happens to come from a curl already, then this says that both sides of this will be 0. But of course f here is in general. And this is also some distinction between Stokes and divergence to keep in mind. So what happens in Stokes is you integrate a curl, you integrate a derivative for a Stokes. But in divergence theorem, you integrate an arbitrary f. And also, it's irresistible to again bring this up that, and your book has a nice diagram of this. All of these follow a basic pattern starting with fundamental theorem of calculus. If you have any function whose derivative is kind of continuous, then f of b minus f of a, which you can think of as a integral on the 2 points, the boundary, is equal to integrating on the interior the derivative. So if you integrate the derivative on a set, it's equal to integrating the original function on the boundary. Now we had Green's theorem in R2, or Stokes say, let's do it in one go. So you have a surface, right, and then it has a boundary. Then we saw that if you integrate, so here the boundary is C, you do a one-dimensional integral of f dr, then it's equal to integrating its derivative on the larger object. So when you take the derivative, you move into the larger object. So in this case, that is the derivative of this object is curl of f, which is another vector, and you integrate on the s. And now divergence theorem, you have a closed surface, you have a potato. The boundary is a closed surface, and integrating f, any vector field on the boundary, is the same as integrating its derivative. And now in this case, derivative of f is this divergence derivative, not curl derivative. And you integrate this now scalar value against the volume inside. You see that they all follow the same pattern. So original function, so this is zero-dimensional integral, just the 2 points, just 2 points. This is an integral on the 2 points a and b. This can be actually made mathematically precise. And this is an integral on one-dimensional object. So integral, let's make it simply. Integral over a zero-dimensional object of a function f is the same as integral over a one-dimensional object of its derivative. So what is the Stokes theorem? Stokes, and this is divergence. This is integral over one-dimensional object, this is the curve, of some vector f is equal to integral over one dimension up, two-dimensional object, which is the surface, of its derivative. And in this case, derivative is curl, but remember curl is in terms of partials. And now here you already start with an integral over a 2D object, over the shell, the boundary, and it's equal to integral over one dimension up. So this will be 3D object of its derivative. And in this case, the derivative is divergence. And if you wonder if we can move to dimension 4, 5, and 100, that's actually the case. There is this deep theory of manifolds and differential forms, and all of these, Green, Stokes, divergence, end up looking like this. So if you integrate a differential form over the boundary of some object, some manifold, it's equal to integrating over the manifold itself the derivative of this differential form. So, and in that world, this is called the Stokes theorem, and it includes all cases starting with fundamental theorem of calculus, Green's, Stokes, and divergence. So all of them are called just Stokes theorem, and it becomes compactified into just this elegant formulation, which you never need on the final exam. So that's it. That's a whole semester of multivariable calculus. Congratulations for hanging on this far, and good luck for your final exam.